Welcome everyone to this week's One World IAMP Mathematical Physics Seminar. For those of you who might be joining us for the first time, this is the regular series of seminars organized by IAMP, International Association of Mathematical Physics. We encourage you to join our mailing list to be informed about upcoming seminars. And also, if you want to join IAMP, there will be information about it in the chat. So please have a look. But now let's go to the talk. So today it's my pleasure to welcome Owen Gwilliam from the University of Massachusetts Amherst, and he's going to talk about from Feynman diagrams to commutative diagrams. And let me just remind you that this meeting is recorded, and you will be able to watch it after the seminar. So Owen, the floor is yours.
Okay, thank you so much for the invitation. If somehow you want to see me, my face, there's actually two me's in this gallery, and if you want, you can pin me on the side to have a picture. There's the one where I'm got the floral pictures behind my head. Okay, so thank you so much for the chance to talk. Let me try to place myself in the landscape of mathematical physics a little bit before I get to the main subject of the talk. So maybe I should say that I tend to think about field theory, like Lagrangian type field theories, but connected with tools from homological algebra and sort of category theory. So maybe I want to start by sort of raising a question that bothers me anyway, and that motivates a lot of my thinking, which is when you learn about classical field theory and quantum field theory, it's quite obvious that analysis is relevant, differential geometry is relevant, maybe some basic representation theory of Lie groups. But in the last couple decades, some other areas of math that are less obviously connected with field theory have started to make their presence felt. Things like category theory and some very sophisticated constructions from algebra, like homological algebra and operads. So the question, sort of a broad question that interests me, is why does QFT connect with what I might call higher algebra? So things like category theory, quantum groups, other subjects like that. So let me just list some examples of how these topics relate. So I'm going to put physics on one side, algebra in a very broad sense on the other. So very active area of research in some parts of math and physics are certain two-dimensional topological field theories, known as the A and the B models. And these are supposed to be related by something known as mirror symmetry. There's a lot of physics work on this. In mathematics, this has to do with homological mirror symmetry. So let me do the pre-homological thing. So there's things like quantum cohomology, which is some interesting deformation of ordinary cohomology. And there are other examples like polyvector fields. You don't need to know what these are, but I just want to put some words on the page. So there's things like Gerstenhaber algebras, which are a rather fancy kind of algebra. Other corresponding things that are even more sophisticated, and this is the homological mirror symmetry conjecture of Kontsevich, involves things called A infinity categories, like the Fukaya category of a symplectic manifold, or the derived category of coherent sheaves of an algebraic, projective algebraic variety, say. So these are pretty sophisticated objects here in math. It's been a lot of work to make them be well defined, and to the fact that they're connected has been shocking to algebraic geometers and symplectic geometers. Okay, so that's one example. In addition to TFTs, there's 2D chiral CFTs. And in math, these are often studied in terms of the vertex algebras of Borchards, and lots of other people have worked on it subsequently. Frankel, Lepowski, two Frankels actually, and many others. It's a very rich topic in representation theory now. For three-dimensional field theories, they're topological, like Chern-Simons theory or Rosansky-Witten theory. There's parts of math, things like braided monoidal categories. Again, you don't need to know what these things are, but you might have heard these words, like the representations of a quantum group. And somehow these are supposed to be related to these 3D TFTs. And these have led to very interesting knot and three-manifold invariants. So this made topologists really happy. Representation theorists love this, topologists love this. Physics suggested these two topics were related, which was kind of surprising to people. And nowadays, there's a lot of energy around some four-dimensional field theories. I'm going to just mention a topological field theory, or family of topological field theories, advertised by Kapustin and Witten. These are gauge theories. There's other examples, but I'll mention this. And this is supposed to be related to the geometric Langlands correspondence, which is a really central endeavor in representation theory these days. So this is I think if you'd ask somebody to predict some of the consequences, relationships between QFT and mathematics in the 1970s, they would never have guessed this kind of thing would have happened. So I think it's interesting to ask, like, what's going on? Is there some way to make this systematic and less ad hoc? At the moment, it's a little bit ad hoc. People make educated guesses about how the algebra should go. So I'm going to proffer a partial answer. It certainly doesn't answer this question I raised totally, but that there's a conduit to get to higher algebra. So things like category theory from Lagrangian field theories. So here's maybe the first pass at the main goal of the talk. There's an intermediate class of objects, themselves a kind of higher algebra object, but known as factorization algebras. So these, I should mention, these were introduced by two mathematicians, Beilinson and Drinfeld. And then it's been developed much further by people like Dennis Gates-Corey, who is a sort of acolyte of these two, who works on geometric Langlands. Jacob Lurie, who's a topologist, and a category theorist. Two topologists named David Ayala and John Francis. People like Kapranov, like Kevin Costello and me, and some others. So, and what Kevin and I show in one precise sense, and this is part of, you have to narrow down what you mean here, and I'll talk about this in just a moment, is that if you take the observables of a field theory, then it produces a factorization algebra. This is sort of, I would claim that I think this happens quite generally. Kosh and I have been exploring it in the setting of Lorentzian field theory for, say, perturbative AQFT. Kevin and I did it for things in Riemannian signature. So I sort of expect that it's a general principle that for some aspect of Lagrangian field theory, you get a factorization algebra. And then lots of people in mathematics have developed like many tools for taking a factorization algebra and producing, say, categories from them. So there's lots of ways of getting from this kind of higher algebra to other forms of higher algebra. So yeah, there's this sort of conduit, pipeline you can follow. So the main goal of the talk today is to introduce you to factorization algebras and why they sort of are reflective of the structure of observables of a field theory. And this particular connection that you can take a field theory, which will construct perturbatively using, say, Feynman diagrams, produces factorization algebras, which are some interesting kind of commutative diagram. Okay, so that's the first pass at the kind of tentative answer. So this is a tentative answer. To the question that there's a kind of higher algebra reflective of field theory, and then you can use fancy math tricks to get to other versions. Okay, so let me try to hone in on this observables arrow a little bit. So I'm going to state the result as a kind of, in a sort of fuzzy way, and then try to make it a little more, help you understand a little more precisely what I mean. But if you want a really detailed discussion, so let me state the thing first. So for a classical field theory called script T on a manifold M, if you want, you can think about phi4 on R4, or you could think about Chern-Simons theory on an oriented 3 manifold, your favorite conformal field theory on a 2 manifold. The observables form a kind of factorization algebra, but it's actually a commutative factorization algebra. On M. So I should have said something earlier. A factorization algebra is a local to global object, like a sheaf, basically. So it lives on a space. And for a quantization of this field theory, if it exists, so let me change that to if a quantization. If a quantization of T exists, then its observables, the quantum observables, form a plane, non-commutative, I mean, factorization algebra on M. So if you want the sort of slogan version of this, well, maybe I should raise a question first. So a question you might ask first is, what do I mean by classical field theory? So I'll need to spell that out. And you might also ask what I mean by a quantization. So here, I'm going to mean a Batalin-Vilkovisky quantization. So I'll talk about that in a moment, but it's a way of approaching field theory. So the slogan is that BV quantization, so I'm going to say BV instead of Batalin-Vilkovisky. So BV quantization is deformation, quantization, if you want, of factorization algebras. And I should emphasize that this is inspired by Koncevich's deformation quantization work. Especially as it was explained and developed by Cattaneo and Felder. So Cattaneo and Felder explained how to see Koncevich's work as quantizing, doing a Batalin-Vilkovisky quantization of a sort of two-dimensional field theory. And if you take their work and you plug it into this setting, say the setting that Kevin Costello and I developed, it's a sort of is what they did. And so this is some systematic generalization of their work. And so you don't just have to do it in the dimensions they're working in, you can do it in other dimensions. If you wanted to study Yang-Mills and 752 dimensions, it would work here if you could quantize it to give you a deformation of factorization algebras there. So should maybe remark as well that these people like Koncevich, for instance, predicted this meta theorem not for general not for general field theories, but for topological field theories, where factorization algebras are something known as EN algebras, or algebras of the little n desk operad. So you don't need to know what that is. I'm just saying that there was a version of this meta theorem predicted ahead of time, and we found that in fact this point of view worked for a broader class of field theories. Okay. So I still need to tell you what a factorization algebra is, but let me make one more remark that's maybe orienting. I don't know what people's favorite kinds of field theories or versions of quantization are, but when Kevin and I realized this, we do have to pay a price. We're not going to get all the things you might hope out of a quantization. So first off, in the setting we work in, H bar is a formal parameter. So the quantization is built in modules over formal power series in H bar. Everything's a formal power series of H bar. And quantization for us is perturbative in nature. So we quantize perturbatively around us. You need to pick a solution to the equations of motion of the classical field theory. So just bear that in mind, that these, just like in Koncevich's work on deformation quantization, you're going to get a deformation that has that kind of flavor, a deformation over power series in H bar. Should also mention I love to be interrupted and have questions, so please feel free to interrupt and redirect the talk to your whatever's on your mind. It's more fun to have a dialogue than a monologue. Okay, so let me just briefly elaborate a little bit on what I mean by field theory. I'm not going to elaborate as much as I want because I want to spend the bulk of the talk on factorization algebras. So we mentioned that we work on this thing known as the BV formalism. So let me just give you some orienting remarks. I could give a very long talk, many talks about BV formalism just on its own, but just to place it in the universe, it's an extension and enhancement of the BRST formalism. So if you know what that is, you know that in some sense it's needed, as much as you believe in the word need being applied to things like physics. It's needed for gauge theories like Yang-Mills. If you want to do something like supergravity, which I think was a motivator for Patalin and Vilkovitsky and other maybe exotic theories. But you can, of course, apply it to any Lagrangian field theory you like. It's a formalism that is quite general. A crucial thing about it, if you've ever seen BRST, you'll be expecting this, is that it uses homological algebra. So let me just remind you a very little bit about what homological algebra is, in case you don't, you aren't blessed to use it every day. So just a quick reminder about homological algebra. There's a thing known as a cochain complex. And what is that? It's a sequence of vector spaces, or if you're adventurous, maybe some kind of topological vector spaces or abelian groups or whatever. So big V is for vectors. That's a 1. It's a 2. So here's my sequence. There's a vector space called V minus 1 or minus 2. It's labeled V minus 1. So it's if you want a graded vector space. And then there's a linear map that increases the degree by 1 each time. So there's a map D from V minus 1 to V minus 2, from V minus 1 to V0. And the key property is that if you go move twice, it always equals 0. So when you go from V minus 2 to V minus 1 to V0, this composite map is the 0 map. Which means there's a thing called cohomology of this data is a bunch of vector spaces. The kth one is the kernel of the map out of VK modulo the image of the map going into VK, which this image is a subspace of the kernel by this property. Okay, now my reaction when I first met cochain complexes is, why would anyone want to do this? But over time, you discover that they're quite useful. It feels like a really non-obvious thing to do, but these play a central role in topology, but appear in lots of places, but appear naturally even in geometry and analysis. So let me give you a few examples. So one example is something known as the de Rham complex of a smooth manifold M. So I'm not going to elaborate too much on this, but I'm hoping it jogs maybe a memory. So if it's an n-dimensional manifold, you've got the 0 forms, the 1 forms, all the way up to the n forms. And for instance, the 0th cohomology of this, the 0th de Rham cohomology of M, its dimension is equal to the number of connected components. So the simplest cohomology knows the most basic topology of M, and the higher cohomology knows more interesting things about the topology of the smooth manifold M. The de Rham complex shows up all over the place in physics as a place where things like charges live. And there's lots of variations of it, like with flat vector bundles that lets you see more subtle geometry and topology. There's a cousin of the de Rham complex known as the Dolbeault complex, but it depends on having a, say, a complex manifold. So I'm not going to tell you what it is, but I will tell you that the operator is this del bar operator, this version of things that captures whether it characterizes holomorphic functions. So these are all the space of holomorphic functions on X. So the zeroth cohomology of the Dolbeault complex tells you what the holomorphic functions are on your complex manifold. The higher cohomology knows more subtle things about the complex geometry of the manifold. Maybe I should remark that this operator D, the exterior derivative, this operator del bar, they are elliptic in nature. These are what are called elliptic complexes. And maybe just, so these are, sorry, so these are elliptic complexes, which is a natural home for index theory, like the Atiyah-Singer index theorem. So there's lots of wonderful results about elliptic complexes, the generalized results you know about elliptic operators. But let me point out that any differential operator, let's say linear differential operator, I should say, D on a manifold M gives you a two-term complex. If you want to be really silly about it, there's a bunch of zeros. So you could think about studying any differential operator as sort of studying some cochain complex. A good example to bear in mind are the wave operator or a Dirac operator. These are very physically relevant ones. Okay. So secretly, if you've been doing any linear algebra, you've also been studying chain complexes. So maybe as an orienting remark, in a BV field theory, when you do field theory in the Batalin-Vilikovsky formalism, the fields, so the sections of some vector bundle, form a graded vector space. Every field has a ghost number, if you want, which is its cohomological degree. And if you impose the linearized equations of motion for your theory, so we call these E, it's the graded space of fields, you have a cochain complex. So I'll put Q for the linearized equation of motion. Q because it comes from the quadratic term of the action functional. Okay. So in the BV formalism, you're sort of working in a setting where chain complexes show up very naturally. Okay, so in the meta theorem, to make the meta theorem a theorem, Costello and I restrict our class of theories, work with BV theories whose linearized, so that if you want the underlying free theory, whose linearized complex is elliptic. And that's so that we can use all this nice analysis around elliptic operators to do the renormalization. So we use a heat kernel style renormalization framework. The sort of
that then
yeah.
make Within Euclidean.
Yeah, exactly. So these are sort of Euclidean theories. So our theories, our examples are in Riemannian signature.
And may I ask a question?
I love questions. Please.
Yes, if it's in the Riemannian signature, then does it satisfy the Ostrander and Schroeder axioms such as reflection positivity?
So I've never tried to check that for our examples. We don't impose that as a requirement. We don't impose reflection positivity as some kind of requirement. I think it'd be really nice to see how those ideas interact with what we do.
But in order to recover the Minkowski signature, we need these properties very much. Like we need
Absolutely. I totally agree. That is something I haven't tried to do. I think it would be really important, but I don't have anything useful to say about it. I don't have an answer, I guess. I agree. It's something we should try, or somebody should try.
And what space-time dimensions are you working on? Is it applicable to 4 dimensions?
Yes. This is all
Okay.
perturbative, like I said, and it works in sort of lots of dimensions. So you can do examples. You can do Euclidean Yang-Mills. You can do Chern-Simons theory. You can do Euclidean 5-4 theory. You can do, if you wanted to do some crazy high dimensional field theory, you could do that too. The main thing is that we need this ellipticity here to get things going for our constructions.
I see. Thank you.
So yeah, so there's this meta theorem I stated. You can write a precise theorem if you make precise what class of field theories you're working with, because you need to do quantization, you need some sort of renormalization process, and you need to set up the whole BB formalism. So to do that requires making some choices, and this is more or less the setting we work in. So there's a version of the meta theorem that is a theorem, and we have a book about this. Right now with
And by renormalization, do you mean the renormalization scheme of Kenneth Wilson by introducing cutoffs?
Yeah, we do something in that flavor. We actually do something with like an exact RG flow. So maybe Polchinski style.
Because I'm more inclined for Epstein-Glaser causal perturbation theory. That's what I'm more in favor of. But
can you wait just 1 minute then? Like literally, I'll make a comment about that in just 1 second. Okay. So with Kasha, we're writing. We've written a paper and we're sort of tidying it up right now. So we work in the setting of perturbative AQFT of Friedenhagen and Kasha and Brunetti and other people, and use Epstein-Glaser renormalization to get a version of this theorem.
I see.
In Lorentzian signature. So anywhere, I think, a lot of the details change the way we do things, like under the hood, some of the details change quite a bit, but there's a version of this meta theorem that works. So you get a factorization algebra, and we'd like to explore, and we'd love to talk with other people about this, what this sees about the AQFT point of view, because you'll find that factorization algebras are a little bit different than the AQFT setup, and it's interesting to ask what the relationship is. So I do think it's a meta theorem. I think it applies very broadly, and there's 2 separate settings where there's a version of this meta theorem that is precise mathematics. Cool. So now, after talking for 30 minutes, that was my extended introduction. I'll tell you what a factorization algebra is. So this would be part 1. That was part 0, factorization algebras. I liked your questions a lot, Vinchul, so please keep asking questions. So let's think about a manifold M. And now think about its collection of open sets.
And does the manifold have to be compact, or you don't have to, at least locally compact, and you don't impose any restrictions?
Finite dimensional. I mean, you can, this definition I'm going to give works on a topological space or even on a Grothendieck site. The notion of a factorization algebra doesn't depend, it's a very general notion. It's much more general than the field theory. It's all like a sheaf. It's some very general construction. I'm going to talk about finite dimensional manifolds for concreteness. But okay, so I'm shifting gears. There's no field theory for the next little bit. There's just factorization algebras. I just wanted to find this piece of mathematics.
Okay.
Yeah, but think of your favorite manifold. I don't know, the two-sphere or the real line, or I don't know, an exotic R4.
Yes, R4.
Great. So if you have a manifold, there's the open sets inside of it, which form a partially ordered set by inclusion. And there's lots of operations you can do with open sets. So now let me define, So we define what I mean by a pre-factorization algebra. So a pre-factorization algebra F that's on M and taking values in some category you like. In a category. And so I'm going to say, sorry, let me not be so general. Let me say in the category of vector spaces, or if you want in chain complexes. Chain complexes are what I actually want in the long run, but you can just think about vector spaces for concreteness, for the sake of concreteness. Consists of the following data. So for each open set, U inside of M, there's a vector space or chain complex, F of U. For each inclusion of open sets, so U sits inside of V, there's a linear map. So, you know, picture, I don't know, there's some big open set V, and inside of it, there's some little open set U. Then there's some way of mapping things that live in U into things that live on V, extending them if you want. Now here's the really interesting bit. For any finite collection of opens, but that are pairwise disjoint, UN, all inside an open set V. So again, picture V here, and you can picture a bunch of smaller open sets, U1, U2, U3. There's like a funny face, I guess. A linear map. So from F of U1, tensor F of U2, F of UN to F of V. So this is why we use the word algebra. If you have something on U1 and you tensor something from U2, they combine, and something from U3, they combine or multiply to give you something on the big open set V. So this is the kind of multiplication structure, if you want. So this is the data You have a way to extend. You have a way to extend. And you have a way to multiply. And so then they need to satisfy some conditions, satisfying sort of a kind of associativity. Maybe Mish just satisfy. Let me just say what it is rather than try to give it a name. Satisfying that if U is contained in V is contained in W, then the compositions, there's of course a map from F of U to F of W. And I want this to commute. You know, if I want to extend, sorry, that should be clearly a U into V. These are the same, or they can be the same up to coherent homotopy if you want. And if you have similarly a collection of UNs that are fitting inside of V1s through VKs to W, I'm just going to draw a picture. So if I have W out here, V1 and maybe V2, U1, U2, U3, U4, I could either multiply the things from the inside directly up to W, or I could first multiply them into the intermediary ones and then multiply them from the V's into the W. That's the same. And the last is a kind of, I want it to be equivariant under relabeling. So let's go back to this picture here. The way these open sets sit inside of V doesn't care about the labeling. There's just the geometry there. But when I need to write down this linear map, I put labels on them. So what I want to say is that if I called this U2, U3, U1 instead, if I change the labeling, that permutes the order of the tensor product here. And so I want the map, you know, the permutation of the ordering and then mapping up into F of V to commute. The labeling shouldn't really matter. So you just need to show that, yeah. That just has to do with the geometry and not the ordering you put on the open sets. Okay, so that's a pre-factorization algebra. That's a lot of information. Let me do the 1D case really quick for you. Man, I am not very, I'm too chatty. Okay. Really quick. So let's say that M is the real line. I'm going to show that every associative algebra produces for you a pre-factorization algebra. We call it F of A on R. So I'm going to give you guys a pop quiz. So here's the real line. If I pick an interval in the real line, then F of A needs to assign to this interval a vector space. What vector space should it assign? If I want it to, you know, have something to do with A. Was that you, Eli?
Yeah.
Good guess, Eli. That's awesome. Okay. Now suppose, so for any interval, I'm just going to assign A to it. So now imagine that I have two intervals. I have I and J, and I have them include into a longer interval K. So I need a map from FA of I, tensor FA of J, to FA of K. Now, I'm going to say that this is isomorphic to A tensor A. FA of K is isomorphic to A. So Eli, you've got a harder problem to answer now. What should this map be?
Multiplication.
Woo! Okay, good. So if I have two intervals to a bigger interval, I just use the multiplication map of A. And it's a fun exercise to show that if you had 3 intervals, there's 2 different ways, going into a really big interval, there's 2 different ways they could be contained in 3 intervals going into a very long interval. I could either factor the inclusion through something like this, or I could factor it through this instead. And you can see that these 2 different ways of doing it encode the associativity of the multiplication. Okay, the fact that it satisfies the axioms of a prefactorization algebra come from that. Okay, so you should think about a factorization algebra on the real line as something like a generalization of an associative algebra. There's lots of similar exercises. All standard algebra, things with modules and bimodules has some analog in terms of factorization, prefactorization algebras. Let's talk about 2D pictures really quick, 2D examples. You might focus on pictures, the analogs of intervals maybe being disks. And you could think about how something in here multiplies with something in here to give you something in here. So this should remind you, I hope, this should be reminiscent of OPE type pictures. Sort of think about something supported in the center of the disk, and the center of the disk can be expressed in terms of an observable that depends on the bigger disk. And so I should say that in the 2D setting, there's 2 kinds of algebras, higher algebraic structures that show up naturally. If the size of the disk is irrelevant, so f of a little disk, of course, maps to f of a big disk. This is always an equivalence. And f, 2D, that means m equals R2. Then f encodes an algebra over the little 2 disks operad E2. You don't need to know what that is, but it's something that topologists care a lot about and have studied it in depth. And so this basically means that 2D TFTs, since they don't care about the size of the observables, give E2 algebras by our meta theorem. If the multiplication instead varies holomorphically, as you move the disks. So you could imagine these are now disks inside of C. If you identify R2 as C, you could ask, this is a point Z and this is a point W. If the way that the multiplication depends on Z and W holomorphically, then F encodes a vertex algebra. And this picture I just drew up above really can be identified, that you can extract from it the OPE, the vertex operator map, from that. So in this sense, so you can produce vertex algebras from chiral CFTs this way, if they're at least formulated in a Lagrangian way. And there's some really wonderful work by C. Lee, particularly, really putting some of these ideas to use in the setting of questions in chiral CFT. Okay, so I'm really cutting this up short. Please.
Interrupt things more. The little disks operad is an operad of topological spaces.
Yes.
But we're dealing with vector spaces. So what did you actually mean?
Well, oh, I see. Yeah, sure. So if you you can take the operad of little disks, and if you take chains on it, you get an DG operad, an operad in chain complexes. That's one thing you can do. So yeah, that's what I would do. If you just take H0 of the chain complex, then you just get actually the commutative operad. But
which would be exciting.
Yeah, but if you do the whole homology, you get the Gerstenhaber operad. That's a very interesting operad. But yeah, by E2, if I, in chain complexes, you just take chain the say singular chains or something on the spaces. I'm not saying this is totally easy to prove this sort of thing. But it's true, and it's been written down now very carefully. So maybe I should say this is a theorem. This is a theorem of Chris Elliott and Pavel Safronov, and they do it for EN in general. This thing, some version of it, the first step is by Kevin and I, just to show this sort of, if you put enough hypotheses carefully about saying what you mean by varies holomorphically, we explain how you get a vertex algebra in our book. And then C has really applied these kinds of results in a really interesting way. Okay. Any other questions? Those are great questions. So I've told you so far what a pre-factorization algebra is. A factorization algebra, I'm not going to give you a precise definition because I am running out of time. And it's a little bit technical, but it's whatever. Is a pre-factorization algebra in which the value on big opens is constructed or recovered from the value on small opens. So the idea is, if you knew what happened on disks and how they fit inside each other, you could reconstruct it on the whole big manifold. In technical terms, it's a co-sheaf in the Weiss topology, which is a topology you can put on say a manifold. It's a Grothendieck topology you can put on a manifold. And let me just remark that conceptually, what it means is that the requirement, this Weiss topology just says you need to know all the endpoint functions. Remember, this thing is, F is supposed to be like the observables of the theory. You need to know all the endpoint functions to know the global observables. That's all this is saying conceptually. Okay. So I have.
You just need to know all the endpoint functions.
Just need to know. That's, yes, exactly. You just need to know the endpoint functions. That's exactly right. Okay. Now, I have 5 minutes, so I'm just going to sketch out a final comment about an application of this, where I can say something kind of punchy relatively fast, although I'm not going to obviously give any kind of proof.
So you're talking about some kind of a reconstruction theorem?
Yeah, exactly. If you know all the local OPE type structure, you actually, on a manifold M, then you can know the value of the global observables on M.
I see.
Yeah. So I want to talk about Chern-Simons theory, and there's maybe just really quickly two main ways in which factorization algebras have been used to study Chern-Simons theory that I know of anyway. The first is some work by David Bensvi, Adrien Brochier, and David Jordan. And so I'm going to say something that's going to be a little bit cryptic. I apologize. If you take the category of representations of a quantum group, which you could think about as some categorical version of an OPE algebra. So this is an example. This is actually an E2 algebra, but not in vector spaces in the setting of categories. This is braided monoidal categories. Then it determines a factorization algebra on oriented surfaces, so two-dimensional manifolds. And what they find is, and they recover by using this factorization method, the combinatorial quantizations of Chern-Simons theory due to Alexeyev, Grossa, Shamras, and some others. Those are the names I know. So they give a new construction of these combinatorial quantizations just using this factorization technology. There's like no physics in this case, it's just doing algebra, but it's really neat that it gets back these answers that these other people found by more physical type of thinking. And then I should mention that perturbative Chern-Simons theory was constructed carefully so in this BV type of way by Axelrod and Singer, that's the Singer of the Atiyah-Singer index theorem, and independently by Kontsevich. So this produces, by the theorem with Kevin, by taking observables, gives you some three-dimensional algebra. This algebra depends on three-dimensional space. And that's been analyzed by what this E3 algebra looks like. It's been analyzed by myself and Costello and John Francis. There's general machinery due to, say, Jacob Lurie, that if you have an E3 algebra, you can take, say, A, you can take its category of left modules. And Jacob shows that this is always a braided monoidal category.
Excuse me, what is E2 and E3?
Yeah, so En is this operad of little n disks, and it means that you have multiplication, which means you have a multiplication A tensor K to A for any configuration of disks, non-overlapping disks.
What does it mean, little?
I don't know why they say little.
Huh.
Because there's one disk, and inside that there are relatively little disks, smaller disks.
So there's this big outer disk, and then there's K littler disks inside of it. And for each way of putting K little disks that are non-overlapping in a big disk, you have a multiplication. And it varies in that family, like in a locally constant way.
So is it important that these, so this is the two-dimensional, this is adapted to two-dimensional theories, is it?
This picture is adapted to two-dimensional theories because I only know how to draw the two-dimensional case on my iPad. But you can imagine, right, like having three balls sitting inside of three-dimensional space. Or
so n disk means an n-dimensional object.
Yeah.
Okay.
Yeah.
So n disk means a ball or a product of n disks. What is?
It means an n-dimensional ball.
N-dimensional ball. Okay.
And there's a non-trivial fact, which is that being an En algebra is the same thing as having n distinct homotopy associative multiplications that commute up to homotopy. But so if you want, it's n-dimensional algebra. It's algebra where you're allowed to multiply things in n different directions. Yeah, sorry. I was trying to being a little too imprecise, and I apologize for that. But that I should have elaborated on that. I had one last little thing to say. With a little bit of careful work with factorization algebra technology, you can explain how to take from a ribbon category, a braided monoidal category like this. You can get Reshetikhin Turayev link invariants. So there's an existing way of doing this, but you can actually understand it in a more refined way using this stuff. So there's this pipeline that starts with Chern-Simons theory as constructed by Axelrod, Singer, and Kontsevich. You use our technology to get an E3 algebra. You apply some general machinery to get a braided monoidal category, because it always works for E3 algebras. And then you can use that data to get the link invariants. And so there's this rigorous pipeline that goes from Chern-Simons theory to Reshetikhin Turayev link invariants, sort of explains where they're coming from. And this factorization technology plays a crucial role in that construction. So I think, so to me, that's been a missing piece in my understanding of how math relates to topological invariants, like link invariants come from field theory. The original Reshetikhin Turayev construction, while beautiful, is a little bit ad hoc. It just starts with a braided monoidal category that they claim captures Chern-Simons. They don't really directly show how you get it from Chern-Simons, and then they get the link invariants. This kind of fills in that connection. Okay, I'm done. Thank you for listening. Sorry to run over.
Thank you, Owen. Thank you for a nice talk. And yeah, I appreciate detailed explanations and answering to questions. So don't worry about running over 2 minutes.
Okay.
So are there any more questions? So please either raise your hand or unmute yourself and speak.
I have not. I'm under the impression that you have not dealt with the convergence issue of perturbative series that much.
Not at all. Although there are fun, maybe I should say, not in general. In some cases, of course, you can make theories that are one loop exact or something. And so in that case, only sort of a single power of H bar shows up in your deformation, and there's no problem. But that's sort of like, that's sort of a lucky accident, say, like when you do a theory like a BF type theory.
Yes, the kind of thing that I expected was that, like, the perturbative expansion is asymptotic series, and I thought you'd come up with some kind of resummation technique that would make them convergent, so that it will lead to non-perturbative results. That's what I kind of expected.
Well, I'm glad you have so much faith in me, but I would love that. The thing is, this kind of resummation technique, whatever idea, isn't, we're not just working with, say, functions here, numbers or power series. We're dealing with DG vector spaces. So like vector spaces, if you want, over power series and H bar. I don't know a version of kind of resummation that works at the level of vector spaces as opposed to sort of power series. Like, I don't know. I think it's a really wonderful question to ask. Like, how do I take this vector space of observables or chain complex of observables, and when can what would it mean to resum it to get something that didn't involve a power series in H bar? That's a great question, but I don't have a good answer.
Any more questions, comments?
Yes, okay, so this is a kind of stupid question. So one case you don't have to worry about this resummation or anything is just free field theory. It's not my favorite field theory, but is it possible to work out factorization algebra and everything in case of free field theory? Like free scalar field theory, the simplest
Yeah,
case you can
absolutely.
imagine?
So I wrote my thesis about free field theories in the Euclidean signature, and Kash and I wrote a paper a few years ago about the Lorentzian setting, and yeah, H bar there. I mean, we just work with it as a polynomial in H bar, and everything's fine. But you can specialize H bar to a number then if you want.
And do you get some fancy mathematical object out of that, or something simple? What?
Yeah. So let me say, if you pick a hypersurface in your manifolds, your space-time manifolds, that's it. In Euclidean signature, it's just, a hypersurface. Otherwise, Lorentzian signature, you want something like a Cauchy hypersurface. Then from the factorization algebra and this choice of hypersurface, you can recover a DG associative algebra, or an associative algebra if you want. For the free boson, this looks like a big Weil algebra. For the free fermion, it looks like a big Clifford algebra. Sort of the things you would expect. If you do something like Chern-Simons theory for abelian Chern-Simons, then of course you could ask about things not just hypersurface, but could go to lower dimensional surfaces. You could use that data, just like I was just saying in the perturbative Chern-Simons case, to recover, say, representations of U1Q, like the quantum deformation of representations of U1, which is very easy. It's a silly deformation of Z-graded vector spaces. But like that's I think actually kind of a fancy gizmo. It's a braided monoidal category, so it's some kind of higher categorical object.
Okay,
you can also get things like the vertex algebra, the Kac-Moody, the big Kac-Moody vertex algebras this way.
You mentioned the word quantization.
Yeah.
So what? This is a word with many meanings.
Yeah,
so what is the meaning that you use?
So we're doing this Batalin-Vilkovisky quantization. So one way of saying that is that if the choice of action functional S in your classical field theory, so maybe I should say this. In a Batalin-Vilkovisky field theory, if you look at, there's a DG algebra.
Excuse me, what is a DG algebra?
Like DG anything is another way of saying cochain complex. So a DG
okay.
algebra.
D is the differentiation.
Yeah, G is graded. Yeah, differential.
Okay. Okay.
Yeah, sorry to use all this like lingo. Okay, so we have an algebra and chain complexes, a commutative algebra, classical field theory, where the differential is determined by the action functional. Okay, it's in the BV formalism, there's a kind of Lie bracket called the anti-bracket, and it comes from bracketing with the action functional. So it's a little bit like in the Hamiltonian formulation, you bracket with the Hamiltonian to encode the dynamics. So that's the classical thing. We have a cochain complex, and the differential is determined by the action functional. BV quantization means that you deform this differential in a sort of specified way. There's an equation called the quantum master equation that the deformed differential has to satisfy, or the action function has to satisfy. This is akin to, in deformation quantization, asking that your commutative product gets deformed to an associative product such that to first order an H bar, it recovers the Poisson bracket you started with. There's a totally analogous. I can write it on the, actually, let me just write it here I have my iPad. So we have S as an action functional. We have some chain complex, let me call it O classical. And it has a differential, I'll call D sub S classical. And I'm just sort of saying that there happens to be this actually is shifted Poisson via a thing called the anti-bracket. I didn't pick the names, so.
Is there also an uncle bracket?
They're a what bracket?
An uncle bracket.
Oh, anti-bracket. Oh dear.
No, stop, Eli.
Well, you're banned from this seminar. Okay.
Quantization means that we take this thing and we adjoin H bar, okay? And we deform the differential. So we get some new differential, which will look like the classical differential plus H bar modification. So I don't know, some modification like this, some modification like this, where we want D to satisfy the following rule, that if you take two elements in here, A and B, and you just use the multiplication, you use commutative multiplication, D of the product, it almost looks like this. So you can see that there's this controlled way you're modifying the differential, and the way the differential deforms depends on this anti-bracket here. So it's a little bit like in deformation quantization, the multiplication has to deform in a way that depends on your ordinary Poisson bracket. Okay?
Okay, so is it a unique procedure or?
No.
No.
Yeah, so you can see the way we usually do is we start with this and we try to solve this equation modulo H bar squared. There's usually not a unique D1, but you find a D1 that works mod H bar squared, and then you try to solve for mod H bar cubed, so you get a D2. So at each power in H bar, there's usually some freedom of choice. And sometimes you can't do it. Sometimes it's obstructed to actually quantize. And those are usually given by well-known anomalies.
Yeah, so is it, so as I understand, the beefy formalism is interesting if you have a gauge theory. So if you have a classical theory without a gauge invariance, then there is
that's no obstruction. Yeah, there always is a quantization. There's usually something of an obvious one.
Yeah. So I mean, my question is, for which theories this formalism of factorization algebras, BV, etc., is relevant, is interesting? Is it only, I mean, for which classes of theories? Do I understand it correctly that you need some local gauge invariance because otherwise it is not interesting, or am I wrong?
Interesting's in the eye of the beholder. I agree that for most traditional theories that have no gauge type data, this just recovers the well-known answers locally. Like you'll just recover the algebra that the algebra of operators you're used to usually seeing. So you can use this to recover, like I said, the Weil algebra or any kind of canonical commutations relations kind of algebra. Maybe the one nice thing which I didn't emphasize in the talk is that because the value on big open sets is determined by those on little open sets, like if you have an interesting space-time manifold with interesting topology, our process actually tells you what the observables are on that in terms of this sort of local OPE structure, which I think is new even sometimes in the case of traditional theory. So for instance, our methods, if you're doing one-dimensional mechanics, but you do it on where space-time is a circle, so periodic time, rather than just on the line, we actually don't just get back like an algebra on the circle, we get back the Hochschild homology of the algebra. So we know all the higher Hochschild homology of the Weil algebra or the Clifford algebra or of the deformation quantization if it's some interesting target symplectic manifold.
So may I follow up on this one a bit, since we are talking about interesting? So I mean, yeah, I think that's a comment and a question. So for the scalar field, you still have the renormalized BV Laplacian for the interacting case. So there is still, I mean, something which, at least from the renormalization viewpoint, is interesting.
Sure.
But do you think that this could lead to something non-trivial when you glue these things together? So like, let's say I can renormalize things locally, and is there potentially some obstruction into getting a global BV Laplacian from local BV Laplacians?
Yes.
Okay, so that would count as interesting to me.
Yeah. Yeah. No, I mean, yeah, absolutely. But yeah, I don't, right. We could.
So I think maybe the answer to Jan's question is, well, it's not entirely boring for the scalar field if you have interaction, because you have renormalization.
That's true.
So yeah, although obviously the free theory is entirely boring.
I don't think so. I think it's interesting. I agree it's mostly boring, but if you do the B approach even to the free scalar field, it sees non-trivial invariants like the Hochschild homology of the Weil algebra. And I think it can be used.
True. That's true.
Like, you can prove versions of the index theorem using these techniques, which I think clarifies how things like the index theorem relate to physics.
So that's also non-boring.
Right. And that's even for like really pretty boring looking theories. Just, yeah.
Yeah, that's cool. Okay, yeah, Jan, does it answer your question?
Well, yes, it does.
Thank you.
Yeah.
Right, any other questions, comments? The talk is still being written.
I just wanted to point out that I wanted to say who you could read about for this claim. The boring, but interesting global data.
Nice.
Yeah.
Okay, so I think with this we can close the discussion and thank Owen again for the nice talk and answering all these questions. Okay, thank you so much.
Yeah, thanks.
Bye-bye. Thank you.